So thanks, everyone. First of all, I wanted to say thanks for the invitation to speak today, and also to the organizers of the event. I really appreciate the opportunity to speak here at Brain Modes. And just to get started, I wanted, before I talk at all, I wanted to get note that this work is the result of a team of researchers, including Roberto Budzinski, Alexandra Bush, Jackie Duan, and my colleague at Western, Jan Minach. And so this line of research started with analysis of sleep rhythms that were recorded in human clinical patients recorded with intracranial ECOG arrays. So these are sets of electrodes that are placed directly on the cortical surface as part of a mapping procedure for the treatment of epilepsy. And these recordings were analyzed in a collaboration with Sid Cash's lab at Massachusetts General. And we specifically studied sleep spindles, which are 11 to 15 hertz oscillations that are deeply tied to learning and memory. And studied the spatiotemporal dynamics of the spindle, we focused on individual oscillation cycles and then characterized their spatiotemporal structure across this recording array using computational algorithms I had been working on. And when we did this, we found that the individual spindle cycles, when you look across the brain, are organized into a specific spatiotemporal pattern on the whole brain scale. So in the movie I'll show, each dot here is an ECOG electrode, plotted directly on the cortical surface. Normalized potential in the spindle frequency band is plotted in color. The red dot on this channel right here will mark out the time course for the channel in black here. And the other ECOG channels are plotted in gray here. So when studying these spatiotemporal patterns, we found that they formed these repeating rotating waves traveling from the temporal to parietal to frontal lobe, and then back again. So this is 5 cycles of a spindle oscillation in a sleeping human subject. There's no spatial smoothing here. This is just an activity pattern analyzed by our algorithm. So after seeing this, the first thing we were interested in was the speed of these waves. And we observed here that the speeds consistently traveled between 2 and 5 meters per second. So those speeds are really interesting because these fall right within the range of conduction speeds for the long range fibers that connect different regions in cortex. So as we've heard previously, spikes traveling down these fibers propagate at a speed of 2 to 5 meters per second in the same range of speed as those rotating waves we observed. So this suggested a possible network mechanism, but it also raised a specific question. And that was, how does the structure of an individual connectome, like this here, lead to specific emergent wave patterns that we observe on the recording arrays? So specifically, we've observed waves organized into a rotating pattern and also with a preferred direction or chirality. And how can we understand that specific pattern in terms of the complicated network here where there's no major anisotropy? Now, much research, including work from Joana Cabral and others, has utilized weakly coupled nonlinear oscillators on the networks or graphs defined by this large-scale fiber network. These models, however, are difficult to analyze mathematically in terms of this very highly structured graph. And that's especially the case when you have multiple time delays. But I think this is an interesting general question for people doing theory in neuroscience, because it's increasingly clear that the specific pattern of connections in a brain network or in a trained artificial neural net are leading to a specific computation. So today, I'm going to show that a complex valued matrix formulation of the Kuramoto model connects the eigenspectrum of the adjacency matrix to the resulting nonlinear dynamics. Part 1 will introduce an algebraic approach to nonlinear oscillator networks. Part 2 will introduce a geometric approach to synchronization phenomena and time delays that's made possible by this algebraic approach. And part 3 will go to waves that we've observed in single regions of the visual system to understand more about what computations could be done with traveling waves in single regions of cortex. And finally, and if there's enough time at the end, I'll show recent work from my group demonstrating that spatiotemporal dynamics in recurrent neural networks can be a powerful substrate for computation. Before we get too far into the details, I wanted to motivate this in terms of practical applications. So networks of nonlinear oscillators are often studied because they're mathematically tractable. but they've also recently shown promise in practical applications like sequence processing, such as with the Acorn system recently introduced by the group of Max Welling. So now we'll introduce an algebraic approach to nonlinear oscillator networks with these kinds of problems in mind. And I'm going to write on the board, so maybe, can you turn on the lights maybe? Or it might be more visible like that. Okay, so as I mentioned, we were studying the Kuramoto model. And the dynamics of the system are governed by these equations. Let me know if it's not legible in the back, and I can expand my writing to be a little bit larger. Larger? Okay. So this equation specifies that the dynamics of node J in the system are specified in terms of the intrinsic frequency omega, the coupling scaling epsilon, and then the nonlinear coupling with the other oscillators in the network. And now, this is written in the form of a general graph adjacency matrix, AJK. Now, when A is diagonalizable, we can write it as an eigendecomposition in terms of a matrix of eigenvectors V and a diagonal matrix of eigenvalues D. The eigenbasis provided by V could help us understand or even predict the waves that result from the pattern of connectivity here and also the specific pattern of connectivity. But as we're familiar with, making this type of link is not possible when systems are nonlinear, and especially when they have multiple time delays. So what I'll show next, though, is that we can develop an algebraic approach to this Kuramoto system that links AJK, specifically functions on its eigenvectors, to the dynamics. So just to start with this, following previous work, we can change to a rotating coordinate frame here. And set omega equal to 0 without loss of generality. This will make the presentation simpler, but I'll note that while we'll start with homogeneous intrinsic frequencies, the approach generalizes also to the non-homogeneous case. And now, starting from this equation, with omega set to 0, we can study a very similar system. Hard to see the green? Okay, sorry about that. I can bring that back up. Sorry? No, yeah, sorry about that. No, I was trying to highlight this term here, but that's okay. So now the core variable psi in this equation is going to be complex valued. So psi j is going to be complex. And it differs from the original Kuramoto system by this additional term in the interaction term. So what I'll show is that this complex valued system emits an exact solution. And then we'll compare the argument of the elements, we'll compare the argument of psi j to the phases theta j in the original Kerr-Model model. So at this point, it's important to note that these are two distinct dynamical systems. But I'll also show how we can derive an additional analytical procedure to match them up so that their trajectories match precisely, while also allowing us to make analytical predictions from the adjacency matrix here. Okay, so, and I'll make sure to write the next set of equations a little bit larger, but now we're just going to multiply through by I.
Sorry, I have a question.
Yes.
So if psi is complex, then how do you find the cosine and the sinusoid of complex?
That's a great point. So we're going to jump to the Euler form in the next line, but sine and cosine are still well defined when with a complex variable. Yeah, but it's a great point. So now we can apply Euler's formula, and now we can rewrite the system. So now the phase difference in the interaction term up here. So initially these things this looks a bit intractable, right? Because now you have all the information of the phase in the interaction term inside this nonlinear function. But now at the very least, we can express the phase difference in terms of complex exponentials. And this allows us not only to separate these phase differences, but in the next line of computation, we can bring the term containing the node's own phase outside of the sum. Okay. So this is an improvement. We rearrange the terms so that this form looks at least somewhat tractable now. But this equation is still clearly nonlinear in psi. And so this is the important step, because if we take this term here and move it over to the left-hand side of the equation, and then apply a nonlinear coordinate transformation, so we're going to apply the nonlinear coordinate transformation xj equals ei psi j. Then the time derivative of this looks like this. And that, taken together, leads us to this equation for the dynamics in the new variable. This we can rewrite in matrix form. Where I'm denoting vectors and the derivative there. And we can solve. Now, remember that it's the argument of the elements of this expression that we're going to compare with the original Kuramoto model. So we're going to compare the arg of the xj's with the theta j t in the original Kuramoto model. And in addition, it's important to note that we'll utilize initial conditions here. So this is the correspondence of the initial conditions between the two. For all j. So we'll choose random initial conditions for our thetas here. We'll use this form to put the same initial conditions into our complex valued approach with unit modulus initial conditions. So xj 0, the mod is going to be equal to 1. Finally, this solution is defined in terms of a matrix exponential on A here, which is again directly the network adjacency matrix. And in many cases that we're interested in, we can utilize analytical expressions for the eigenvalues and eigenvectors of this, and that allows for a fully analytical evaluation of this complex valued system. Okay. So with that, now we can write out the comparison, or we can compare the two systems. And so we can study the dynamics of the systems in a space-time plot. Here, we're putting time on the vertical axis and nodes on the horizontal. Here, dark colors will indicate values close to minus pi, and light colors will indicate values close to pi. And so in this simulation, the network's just on a one-dimensional ring with all-to-all connectivity. That's the case originally studied by Kuramoto. And this is a numerical simulation of our Kuramoto equation here. Right, so this is just a numerical simulation of our Kuramoto equation in the rotating coordinate frame. And the numerical simulation starts at some random initial condition that we pick, and then progresses to synchronization, which you can see by these horizontal lines here. So the broken color axis just helps you identify really clearly when the system progresses to synchronization, right? So looking now at the analytical expression, we can see that the dynamics in the two cases, even in the range with strong interactions in the network, show similar patterns, with many of the microscopic features of the spatiotemporal dynamics matching up precisely. You can see some small differences here. So for example, these oscillators that are out of phase with the rest of the network in the synchronized state. And you might already be wondering to what extent the trajectories in the two systems can match up precisely. And so in order to study that question, so in order to study that question in detail, we can go back to this form with psi, and we can decompose psi into its real and imaginary parts. So here I'm just breaking up the complex number psi j into its real part and its imaginary part, and pulling out the I there. And note, in addition to the way, because of the way the nonlinear coordinate transformation works, it's the real part of psi. This part is going to be related to the arg of x. And the imaginary part here is going to be related to the amplitude or the modulus of x. So there's kind of an exchange between the two that happens. Now, from this step, we can derive an equation for the dynamics of the real part of psi. I won't go into detail on this, but I'll just provide that we can write down. Can you still see that from over there? Okay. Actually, go. So we can write down an equation here, d psi j real dt is equal to epsilon So now, again, the real part of psi is what corresponds to the thetas in the original Kuramoto model. And here we can see that this differential equation corresponds almost precisely to the original Kuramoto equation, differing only by the term here that has to do with the ratio of amplitudes of the x's. So this would be the amplitude or the modulus of node xk and node xj. So the ratio of the moduli of the node itself with the other nodes in the network. If these are if this ratio is close to 1, that shows us explicitly that the complex valued system corresponds precisely to the original Kuramoto model. So as a specific example here, the initial conditions for the complex valued system have unit modulus and arguments that correspond to the thetas. And so you can see that they're matching up for a specific non-trivial window of time. But this also motivates another step, because now we can advance our complex valued system in specific short steps of time bar sigma. So we can advance this system some time bar sigma into the future, and then apply an additional operator. We'll apply this operator lambda. Which we define to be an element-wise operator mapping the modulus of z, or mapping z, its modulus to 1. So in this way, this two-operator expression can be thought to reduce the nonlinear continuous time Kuramoto system to a discrete map-like description. Note that this is, of course, it's a recursion and not an all-time solution for the Kuramoto dynamics. But importantly, it allows analytical access because we know that all evolution of the arguments of the state vector are governed by the linear matrix exponential operator here. And because of that, we can analyze the dynamics of the Kuramoto system in terms of the arguments of the eigenvectors of A. So we can think about this quantity. Or the argument of the kth element of the jth eigenvector of A. And I'll go into detail on that in the next few slides. But the thing that's just in closing for this part, I think the thing that's important is that connecting the eigenspectrum of a network's adjacency matrix and a specific adjacency matrix, and any graph or one that you might find in the data, it's a very difficult problem for nonlinear systems in general. Here we have one example case that this can be done for systems of Kuramoto oscillators. Okay, so now when we use that complex valued system, this is another example of a synchronizing state that arises in a network with all-to-all connectivity using this operator expression. So this is just a different set of initial random initial conditions in a new simulation. And here you can see that the numerical simulation and the complex valued approach now have very similar trajectories. So the oscillator's specific phases match up precisely in the space-time plot. So the two systems are following precisely the same trajectory. And now we want to use this approach to understand the mechanisms underlying synchronization phenomena. So now in part 3, we'll study a geometric approach to synchronization phenomena and time delays. But yes, of course. Yeah, it's important. Yeah, so the first thing to note is that the size of S or bar sigma here doesn't have an effect on whether you can study the linear operator there and eigenexpand there. But so if we're close to close to a twisted state or an equilibrium, we can be very far in the future, and the trajectories can correspond precisely. But even in chaotic states, like chimera states that are known to be chaotic transients, we can reduce sigma var sigma small and still capture the same trajectory. But that's a great question. Are there any other questions? Quick. Okay. Yes, sorry. Yeah, the key thing is that when the moduli, so we're taking these steps here, and when the moduli are equal, we know that the two analytical forms correspond precisely. So, and a very talented postdoc in my group has been working on this and actually started to do calculations about what we can say about the system near the edge of chaos. But so I'll answer your question by saying that it does correspond precisely in that scenario, even in as related like here the case of chimera states that are chaotic transients. Yeah. So now we can use this algebraic approach for this geometric approach for synchronization and time delays. So in this part, we'll work with an aggregate matrix K that contains information. So we're just compressing information about the adjacency relations and the coupling strength into one matrix. Now, in many cases, we're going to study A circulant, and then we'll expand to the more complicated case, getting the analytical insight there and then expanding the results to data-driven or other graphs. But when A is circulant, as in the case of all-to-all connectivity, we can utilize the circulant diagonalization theorem, which provides us these explicit analytical expressions for the eigenvalues and the matrix whose columns are the eigenvectors of a circulant matrix. And now all circulants are diagonalized by the same unitary matrix. And you can see this here has these columns that are equivalent to a complex DFT basis. And again, I'll present results for circulant graphs, but the results also hold for random graphs where we diagonalize numerically. Now, the first eigenvector from a DFT basis is all 1. So the first eigenvector is 1, 1, 1, 1, 1, 1. And to explain this visualization here, what we've done is to plot the elements of the eigenvector at each node in the network, where each node is positioned along this one-dimensional ring. And as you'll see in a few moments, this type of plot allows you to visualize the specific spatiotemporal impact of each eigenvector on the resulting dynamics. And the insight from this analysis that what we need to study is not the eigenvectors themselves, but the argument or phase of the eigenvector elements. And we'll represent this using this color code here. And the argument of this first eigenvector is all zeros. And I'll show you on the next slide that that's associated with phase synchrony. And the other eigenvectors are the other wave numbers. You note they travel in either the counterclockwise or the clockwise direction. And we can now think of the argument of these eigenvectors as building blocks of the spatiotemporal patterns in the nonlinear Kuramoto system. Now, to study the dynamics of the Kuramoto system, we'll look at the complex valued system, which has a precise correspondence. The trajectory is the same up to machine precision. And we'll study the contribution of the jth eigenmode, which is quantified by this inner product here. So in this example, the network quickly transitions from random initial conditions to synchrony. And when we can project the solution X onto the eigenvectors of K, note the log scale and the heat map here. And we can see that the eigenmode contribution is almost uniform for the incoherent dynamics. But as the network transitions to phase synchronization, the first eigenmode becomes dominant. And you'll recall that the first eigenmode corresponds to this eigenvector with argument all zeros, or the phase synchrony eigenvector. And we can use the same framework to understand the geometry of waves in the network. They're also known as twisted states, where there's a constant phase difference across oscillators. Again, we can see a precise correspondence between the two approaches. And when we look at the contribution of the eigenmodes, we can see here now that the second mode is dominant. So in this framework, these higher modes now represent, again, waves with different spatial frequency. So we've seen this approach can provide insight into phase synchrony and traveling waves, which are interesting canonical synchronization phenomena. But does it also work for more complicated situations like real data or if you have many time delays? So we can also use this approach to gain insight into how heterogeneous distance-dependent time delays affect spatiotemporal dynamics in Kuramoto systems. So to do this, we study the Kuramoto equation now with time delays. And these are just going to model the axonal transmission down the spike. Now, here, utilizing the well-known approximation to turn time delays into phase delays, we can obtain a modified form of our operator expression, where the elements of this matrix W, we're going to do the same thing and compress the information down and into one matrix, and the elements of that matrix W will contain information about the coupling strength, the time delays, and the adjacency relations. So now we can compare results between the simulations of the original Kuramoto model, the time delay Kuramoto model, and our operator expression. And that'll allow us to see the effect of the time delays and the underlying mechanism. So in the original Kuramoto model, we have the synchronizing behavior as before. If you add in distance-dependent time delays, that shapes the dynamics into a traveling wave. This is just one example traveling wave in an individual simulation. You can see here possibly that there's now angled lines in this space-time plot representing the traveling waves. Finally, we can see that our complex valued approach, again, captures a trajectory similar to the computational simulation. Note that this result is obtained under the time to phase approximation, while this is a numerical simulation of the full original time delay Kerr-Moto system. And the advantage of the analytical approach is now that we can understand the mechanism of how time delays shape the dynamics in terms of the spectrum of W. So in the case without delays, W is real in Hermitian. And we can see that the largest eigenvalue, again, associated with the eigenvector representing the synchronized state, leads to that mode dominating the network dynamics. And now we can consider how adding time delays changes this plot. And here, the delay operator here is Hadamard, or element-wise product onto the adjacency matrix. And in this case, both the adjacency matrix and the delay operator are circulant. We started off, for example, with a circulant graph for the adjacency relations, and the time delays are just distance dependent. So they're the same for all nodes. Both matrices are circulant. And what that means is that we know W is also circulant. And that W and A then share the same eigenvectors. This is for the simplified case of a ring graph and on a circulant matrix. But here we can see exactly how the time delays shape the dynamics in the system. So from this analysis, we know that the delays only modify the eigenvalues of the adjacency matrix in this case. That is, we don't change the waves that can occur, but it changes the waves that do actually appear. So you can see now the eigenvalues of W are shifted in the complex plane. And specifically, this eigenvalue associated with synchronization is now shifted to have smaller real part. And this point is associated with the third eigenvector. And when we plot the argument of that eigenvector across our network, the form of this mode is a wave traveling in the counterclockwise direction. And connecting this eigenvector with the largest eigenvalue in real part allows us to predict, again, from the spectrum of W alone, the dynamics that will result. And when we visualize the dynamics of this 1D network, we see the vast majority of random initial conditions indeed evolve to the predicted spatiotemporal pattern with the specific spatial frequency. Now, finally, it's important to emphasize that this analytical approach is defined in terms of a specific graph adjacency matrix and remains at the finite scale. So this allows us to apply the approach directly to the experimental data, like the human connectome. Just briefly, following previous work, we used the reconstruction of the fiber tracks for the connection weights. And then we use the specific distances coursed by the fibers to have an estimate of the time delays. And now we can simulate a Kerr-Moto oscillator at each node using this graph and a specific frequency. So here, for example, we use 10 Hertz. And we can now use a numerical eigendecomposition of this more complicated matrix. And with the same analytical approach, then make predictions about the resulting nonlinear dynamics in the original time-delayed Kerr-Moto system. So on the left here is the top eigenvector, where we plotted, again, the argument of each element of the nodes in the brain network. And again, because it's the argument of the complex valued system that determines the phase dynamics, the argument of this eigenvector tells us the shape of the dynamics. So we can see here, all the nodes are at the same phase, predicting the synchronized state in a network without delays. And then we can see that the dynamics in a numerical simulation matches that prediction. But if we go to a case with time delays in the system, we can appreciate that the eigenvector with largest real part now exhibits an offset in its arguments, which in turn predicts a phase offset in the resulting dynamics. And when we run the numerical simulation, we can see that the addition of time delays results in a traveling wave pattern that matches the analytical prediction. One thing that comes from this, and I think it's important to note, is that this is not coming from any one fiber bundle in the brain connectivity. Rather, it's the summed effect of many time delays, resulting in a macroscopic organization in the network dynamics. So how much time do I have left, roughly? Is it at time? I just want to show really quickly one application of this approach, which is at a different scale. And I think it will be interesting and useful for how we can take these types of analytical approaches and apply them to questions separated from this macroscopic brain dynamics. So I just wanted to mention quickly this point about what computations can you do with waves traveling over single regions of visual cortex. So many people are probably familiar with the retinotopic map. The idea here is that if you have a single region in visual cortex, so now we're focused on the single region dynamic scale, that has a map of everything we see. And if you have some point of light in your visual field, that maps onto some point in the visual cortex, and a neighboring point does the same. And because that creates an orderly and structured mapping from the sensory world to the surface of visual cortex, so the surface of this single visual region, the retinotopic map is a fundamental concept in visual processing. But in different analyses that I haven't shown, we found something interesting when we analyzed these hotspots of activity on the single trial moment by moment level. And that's that rather than remaining static, these points of activity actually create waves that travel across this region of cortex. So what computations can you do with a wave traveling over a retinotopic map of visual space? To understand that, we focused on recurrent neural networks, where inputs project with feed-forward connections into a recurrent layer, where these nodes are densely interconnected, and they approximately follow the pattern of connectivity in visual cortex, so you have some sense of local connectivity. And here, each node here is actually going to be one of the oscillators we've studied, with some minor modifications in the recurrent layer. And network connections in the recurrent layer, again, have strength falling off with distance, and each connection will have a time delay roughly approximating the delays that occur in visual cortex. So then we feed individual movie frames into the network, where the recurrent connections generate intricate patterns of activity in the recurrent layer, right? So now you have a complex natural image coming in, and you're creating this complicated pattern of activity in the recurrent layer. And as we might expect, when we stimulate the network with a point source, it's going to produce a wave of activation traveling outward from the point of input that's via the recurrent connection. So if you stimulate one point here, now you get a wave of activation sweeping across the network. And here's the key idea. Because waves unfold over time as they travel across the retinotopic map, they could provide a neural mechanism for short-term predictions in the visual system. In other words, we hypothesize that waves traveling over a map of visual space can structure information about the recent past for short-term predictions. And so I wanted to show this because, again, we're zooming into the single region scale, but we can point to a very specific type of computation that you can do with waves that might not be evident at first. So I'll just describe this very quickly and in closing, and I'm happy to go into more discussion later. But in brief, what we do is now we have an image input. The image goes, hits the recurrent layer. That creates a complicated pattern of activity. And then we're going to train the network just by learning the linear readouts here to predict the following movie frame. So what this is roughly a complex valued implementation of the reservoir computing paradigm that people use for predicting chaotic systems in physics. So this had been used a lot for predicting chaotic systems, but had never before been applied to natural movie frames. And what we're going to do is, if the network can get so good at training, predicting the next movie frame, you can actually even then take the predicted frame and feed it back into the input. so that you go into closed loop forecasting or an autoregressive mode. And now, even with sophisticated inputs, like a natural movie of someone in a very simplified setting walking across the screen, we find that these types of networks can be trained efficiently on these naturalistic movie inputs. So here's the ground truth movie. Here's the forecast from the network and the optimal hyperparameters. This is the activity in the recurrent layer. And this is the forecast in a network without recurrent connections, just as a control. So, and here we find that the network accurately predicts the natural movie using only its connection weights. So the network here is in closed loop forecasting mode. It's feeding its predicted frames back into its input. So in this case, again, the recurrent connections in this network are creating intricate spatiotemporal patterns that are resulting from the combination of feed-forward input and recurrence. So you're generating waves that are going across this retinotopic map, which at first glance you might expect, well, that's disrupting the visual representation in some way. But here we can actually see that that complex input is what's driving the prediction. And through the mathematical framework, we can show in a precise manner that you can see these ghost legs coming off of the off of the leg there, that those are composed of multiple traveling waves. So the prediction is precisely driven by multiple traveling waves. And so a natural question when considering computing with waves traveling over maps of sensory space is that whether that type of coding strategy would be possible with wave patterns evoked by complex scenes. And we can see here through this mathematical framework that this type of coding is in fact possible. So in conclusion, a complex valued formulation of the Kuramoto model connects the eigenspectrum of the adjacency matrix to the resulting nonlinear dynamics. A delay operator can extend this approach to predict specific spatiotemporal patterns in networks with heterogeneous time delays. And finally, these network models can be used to understand computation with spatiotemporal dynamics in neural systems. So thanks again for the opportunity to visit today, and we'll take your questions now.